Hello, in this video I'm going to go through vectors, and in particular I'm going to go through some basic vector properties and the kind of basics about vectors you should know, but also how to use these vector properties in geometric proofs or to show that certain properties are true in a diagram that uses vectors. So starting off, we want to really look about what a vector is. And the standard definition, which does come from Despicable Me, is a mathematical quantity with both direction and magnitude. So what does this mean in an actual physical form? What does it actually look like? Well, if you had a grid and you was to draw a line going from one point to another, this would be considered to have a direction if you are going from one point to another, so like point A to point B, but it would also have a magnitude in that it is a fixed length. It doesn't go on to infinity, so it's like a line segment. And so this is what we would mean by a vector, and this is how a vector would typically look. Now, another way of showing the notation for a vector is to use a lowercase letter but in bold. And so here we've got the lowercase a but in bold print, and this will be something that you would see in a number of questions as well to describe a vector. Now, this vector can be described numerically, and so the typical way to describe a vector is to use a column vector format, and you may have seen this in translation work. So if we want to look at the vector from A to B, this would be in a column vector 3/4. Or it could be written with the bold print lowercase a also being 3/4 as a vector. A lot of pupils I've seen try to write this as a fraction, and so it's important that you don't do that because a vector is not a fraction. It is a description of how far you need to go left or right, up or down, to move a particular direction and with a particular magnitude. So if you are going to go with your vector to the left or down, then you'll have negative values. So the top value is an indication of left or right, so positive would go right, negative left, and the bottom value is how far up or down your vector goes. And again, positive would go up and negative would go down. Now, it is possible from this sort of information to calculate the magnitude using a bit of Pythagoras, but I'm not going to go into that in this video. But the magnitude of this vector, for example, would be 5, and you could always look that up if you want to do it at a later point. So there are a number of vector properties that we need to look out for and use. So here we have a vector A which goes 1 right and 3 up. And this other vector which I've now drawn goes 1 left and 3 down. Now, because the direction has completely changed but the magnitude hasn't, and these two are parallel, this vector would be called negative A. Another thing that you can do with vectors is you can also decrease the size of them. So this vector here is about half the size of the vector A. It runs parallel, and so this vector would be half A. Similarly, you can have a vector which increases in size. So this vector is going in the same direction as A, but it has twice the magnitude. It's twice as long. So this vector here would be 2A. And in a variety of questions, you may end up having to use these properties. You'll notice that all these vectors, though, are parallel. Even though they've changed direction or increased or decreased in magnitude, they are all still parallel to one another, and that could be an important feature when solving problems. Another vector property is one about addition, where if you're adding two vectors together, like here we've got A and B, what you will get at the end is a resultant vector, which is C. Now, it's important that you realize that we're not talking about the magnitudes, we're actually just talking about the general direction or the vector itself. Because if we were to do the column vectors for A and B, the number work would actually work out, and the vector we'd have at the end would actually be C. One of the ways you can think about this is if you was traveling from one city to another and then to a third city. In the overall, you've traveled from your first city to your last city, but you could have done that directly. And so in which case there was a direct route, and overall your journey has been that same journey. Now I'm going to go on to look at an exam question to do with vectors and some of the kinds of things that you may have to put into practice. So here we have a question which is from a GCSE exam paper, or at least a GCSE exam style question. You're given a lot of information and you're told various vectors from one point to another, and you're asked to work out or find the vector AB in terms of A and B as vectors. So it's important we realize the difference between A and B as points and A and B as vectors using the notations that we previously looked at. So what we want to know is how do we get from A to B? And the only way we can do this is to use the other vectors that we've been given and what we know about them. Now, one way that you can look at this is if you were traveling along roads. and you want to get from A to B, but you can't go directly. You have to go via another route, or you have to take a detour. Well, in this case, if I wanted to get from A to B, the only other route that I can see is to go from A to O, and then to go from O to B. Now, if I am going to do that, what I will have done is I will have had to go against the vector that is already there from A to O. So that would be a minus 2a. And then if I want to go from O to B, well, that was along the line of the vector in the same direction. So that would be plus 3b. So I could write down that the vector AB is negative 2a plus 3b. But I'd probably rewrite this so that I actually had 3b minus 2a. This would then be a bit easier to work with later, and it makes it less likely that I'd make a mistake with any of the negative signs or anything like that. Now, the second part of this question involves the point P, and we're told information about the location of P in terms of a ratio. And so what we need to do in this question is we want to show that OP is parallel to the vector A plus B. Now, this is going to take a little bit more work, but we want this vector here. So again, considering how do we get from O to P and taking a detour, how can we get there? Well, there's two possible routes. We could go from O to B and then back from B to P. But the route that I'm going to take is to go from O to A, because I already know that that vector is 2a, and then because I have the vector A to B, I already know that direction and what that vector is like. I only want to travel this short distance along it. So I know from my previous work that that would be some fraction of the vector AB. Now, because we want to show it's parallel, what we want to find eventually is that OP is some multiple of A plus B. So looking into this now, the vector O to P, that's going to be the 2a from O to A plus 2/5 of my vector AB. Now the reason it's 2/5 is because the ratio is 2 to 3. So if A to B was 5 centimeters long, A to P would be 2 out of that 5 centimeters. And because it's 2/5 of the vector AB, and we know the vector AB from the last part, this is how my vector OP is going to look. Now this will then need a bit of expanding, so being careful here, just making sure you expand carefully, and then this next part about collecting like terms would then eventually get us to the point that we can show with factorizing that OP is 6/5 of A plus B. That is that OP is a multiple of A plus B. Now if one vector is a multiple of another, that shows that they are parallel because they are going in the same direction. They have the same direction, but they just have different magnitudes. And that would be the end of this question. You wouldn't really need to do any more than that, other than write a little bit of a description of what it is that I've just said. The next question I'm going to go through looks at an idea of collinear points. These are points which are on a straight line. Now the first part of this question I'm going to go through quite quickly, in that it wants you to find the vector PB in terms of A and B. So much like before, we have this vector that we want to find. We look for a different route, and so in this case I'd go from P to A to B, and then this would give me my final answer. Now it's usual in a two-part question on this that you'd want to actually use your part A answer again in the next part. So I'm going to be keeping this for the next bit of the problem. So in the second part of the question, it asks us to show that NMC is a straight line. We're told that B is the midpoint of AC, and we're also told that M is the midpoint of PB. These are things that will come in useful later when we actually are going to do this. Now, being collinear points means that they are all on the same line. So what we need to think about is that if this is going to be true, and bearing in mind the diagram is not to scale, so it's just a bit lucky that it looks like they're on the same line, we need to really think about how we're going to show that in a vector form. What is it that we're going to do or need to be able to show to prove that these 3 points are on the same line? So in trying to show that these points are on the same line, we really need to consider that there are two vectors that we're interested in here. Firstly, there is the vector NC, but secondly, we're going to look at the vector NM. And what we want to do is to be able to show that NM and NC are connected in that one is a multiple of the other, or a scalar. Now, once we've been able to show that, that's then showing that they've got the same direction. but what we will find is that they're going to have different magnitudes. The idea of collinear points is that these two vectors share a common point, as in they would both start from n. Now, because they share a common point, if they're going in the same direction and the only difference is magnitude, then they should all be on the same line. And that is what we're going to try and show using the vectors that we work out from here. So to start off with, what we're going to do is going to look at the vector nm, and we're going to go via point P in order to demonstrate what this is in terms of a's and b's. So to get from n to m, you do b plus a half pb, and we already know what pb is as a vector from part A before. And as m is the midpoint, we're only going to want half of this vector. So if we substitute that in, and then we start to simplify and factorize, we end up with that nm is a half of a minus b. Now we're going to focus on the vector nc, and in this case we're going to get 2a minus 2b. The minus 2b is going to come from going from point n to point A, which has gone against the vector 2b, so it will be a negative of it. And then because b was the midpoint of the line AC, it's going to be a plus another a again. If I factorize this, I'm going to get two lots of a minus b. Now what I've shown here is that nm and nc are the same vector but with different magnitudes. And so we'd then write up a bit at the end to sort of explain that we've shown that nc is 4 lots of nm, and so because they are parallel, so they're going in the same direction and they share a common point in n, they are collinear, meaning that these points are on a straight line. So that would be a final stage that you'd put into your exam question, just to make sure that you actually make it clear to the examiner that you do know what vectors would do in order to show that they're on the same line. Hopefully this has been helpful, and you'll be able to go off and solve similar types of vector problems. Thank you.